that elaborate introduction. Let me share my screen and then we begin with the work. You can share, please. Let me get the right one. Yes. Are we able to see my screen?
Perfectly clear. Thank you.
Right. Thank you so much. I've been introduced already. My work is an ongoing work for my PhD work, and it is aimed at detecting lung diseases based on ultrasound image analysis. So why have I focused on lung diseases? Because lung diseases, which include pneumonia, asthma, lung cancer, TB, and COVID, are still among the leading causes of death reported by Forum of International Respiratory Society, whereby globally TB is killing over 1.4 million people, and lung cancer is causing the death for about 1.6 million people, while asthma has claimed over 250,000 people, and COVID-19 is still a serious pandemic. While in Uganda, TB is responsible for the death of over 30 people living with HIV annually. And the mortality due to asthma stands at 27.3 deaths per 1,000 persons, while pneumonia is also still causing the death of over 10% of children under the age of 5, and then the COVID-19 cases are still being registered with a lot of death already occurred. Therefore, there is need for early detection of these diseases in order to mitigate deaths and lessen the burden on our healthcare system. However, the common gold standard detection techniques are pulmonary function tests. However, this one here in a low resource setting like Uganda, this technique is not very tenable because we don't have enough trained lab technicians, and the resources which are involved are relatively costly compared to the setting. We also have medical imaging techniques, which normally are employed by radiologists, commonly are X-rays, computed tomography, and lung ultrasound. But the literature have already indicated that X-rays have got very low sensitivity, and then the CT scan are very radiative, posing a lot of health risks to both the patient and the users themselves. Additionally, they are also less portable and quite expensive. Contrary to that, lung ultrasound is non-radiative. It is very portable, can be performed with the patient beside the bed, and it is fairly inexpensive compared to the above. So that's why now many of our radiologists are adopting lung ultrasound technique. And in the scanning process, the radiologists have two possible places where they can normally place the probe or the transducer. One of the probable places is across the ribs. And if it is placed across the ribs, we always, the image of the upper rib is seen as this bright line. And then in between here, there is always a pleural cavity, a cavity filled with fluid in between the chest wall and the lung, which is always reflected down here. And the lower rib is indicated here, forming what is referred to as a bat sign. But if the transducer is placed obliquely, that is in between the ribs, it is always only the pro line which is seen without the shadows of the ribs and anything appearing. Now, during the scanning process, there are quite a number of image features which are always seen in the lung ultrasound images. Commonly, for a normal lung, there will always be a proline with multiple reflections of prolines which are equidistant from each other and from the proline. And these ones are referred to as the A lines. And this is an indication of a healthy person. Another feature which is commonly seen is the B lines, which are vertical lines radiating from the prolines down to the end of the tube, and they can be many. And this is an indication of a person who is already diseased and most likely COVID-19. While another feature is what we call subpleural consolidation, which is indicated by irregularity of the prolines and thickening, and then a small perforation called subpleural consolidation normally appears. This is also an indication of a person suffering from pneumonia, COVID-19. Another dangerous situation is what we now call lung consolidation or lung hepatization, whereby the lung now shrinks from the chest wall and collapses. This is now an adverse effect of COVID-19 stage. Then another feature which is always seen is a situation where the lung is now filled up with fluid, and we call it pleural effusion. So all these features need to be analyzed and interpreted by a radiologist. So you find that at times the radiologists need to fidget and identify which feature corresponds to a certain class of disease. And at times, the radiologist can give subjective interpretation because these features, some of them are very similar. Only that these ones have selected the ones which can easily be clearly identified. And at times, if the patients are too many, then it becomes very strenuous to the radiologist for interpretation. So to help in this, there is need for an automated approach to detect the features in order to classify these diseases. And with the invention of artificial intelligence, researchers have developed algorithms in the field of medical imaging analysis. And these approaches are two of them. There is classical or traditional machine learning with the use of computer vision, and then deep learning. But for traditional machine learning, the stages which are involved there is that the medical image features are manually or handcrafted, which is quite tedious and needs a person who has vast experience and a deep understanding of the data. And therefore, this traditional machine learning is quite limited in the medical imaging analysis. Based on that, scientists have researched further on deep learning to liberate or to overcome the challenge faced by traditional machine learning, because deep learning can extract and learn medical image features automatically. So, motivated by this approach, selected studies have applied a deep learning approach, most especially using convolutional neural network, because it has a layer which can extract the features both from high level to low level, and then a layer which can do classification automatically. Most notably, we have Bond et al. We use, the authors use pre-trained VGG16 CNN model to classify lung diseases from image frames of an ultrasound. And the classes of the images were COVID-19, pneumonia, and then normal lung image. And they were able to attain an accuracy of 89% with a sensitivity of 96% for the detection of COVID. In the same vein, Christina et al. Did assessment of one of the lung features, which is B-line. And here they were able to detect the presence of B-lines and assess the quantities of B-lines which are there in order to grade the severity of the infection based on B-lines. And they attained a sensitivity of 93%, a specificity of 96% for the B-lines detection, while for severity grading, their kappa was at 0.65, which was a reflection of a substantial grading compared to an expert grading. And while Amida et al. Expanded the work, for them, instead of analyzing or concentrating on image frames, they went to the videos itself, and they were able to detect B-lines features and localize it using a CNN model with LSTM combined with temporal attenuation network, and attain F1 score detection of 0.81 with a localization of B-lines and with an accuracy of 96%. Now, much as this work have attained substantial accuracy and perform better, there are some existing gaps which still exist. Find that most of the work and others which I have not put there, the classifications of the disease are based on lung ultrasound image frame. While for video analysis, the focus was only on B-lines, yet there are other features in the lung which are indicative of lung diseases. And apparently very little honor work done on multiple lung diseases with a clinical acceptable accuracy. So therefore, our long-term goal for this work is to develop a model for detecting lung diseases with a clinical acceptable accuracy, but using our local available data set. Because one of the challenges which is always experienced by most of these machine learning algorithms, especially deep learning, is the clinical validation. You find that an algorithm trained on one particular data set in a different country where we have a lot of data variability may fail to perform to the expected accuracy when it is taken to another setting. So therefore, our long-term goal is to have our local data, and we develop model based on that. But for the start, we have used public available data sets, and which we have obtained from these two sources. And in the process, we downloaded the ultrasound videos and extracted image frames from each video in such a way that all the frames would be in a respective or in its own folder. And then we went through each of these image frame folders to identify images with relevant and significant features only, which had already shown there. And at the end, we were able to have 4 classes of images: COVID-19, pneumonia, other lung diseases, and then normal lung images. And a total of about 1,433 images were taken with our dataset distribution indicated here. And the sample images which we got from the extraction are all indicated. For A was representing a normal class, then a B was representing COVID class, C was from a pneumonia class, and then D was from other lung disease class. And clearly, we based on the principle that any other appearance than the normal means it is other lung disease, which had no specification based on the author's metadata. Then we use this data to train a VGG model. And why we chose VGG model? One, it was pre-trained already because the training time of the trained model is always shorter. We just need to do some retraining of the last few layers. And this model of the model we use outperformed the rest and had the best accuracy, as we're going to see down there. So, and in that same process, we first started by splitting the images into train and test sets, the ratio of 80 to 20%. And from the training data, we got a validation data to check on the model performance. And we realized that the data set was not diversified enough. We did some augmentation and we got available data. And during the training, some key parameters which we used were here. We first of all resize our image and then use a batch size of 32. We fine tune the last 5 layers of the VGG model, leaving us with the trainable parameters of about 7.1 million and non-trainable parameters about 7.6. And the optimizer we use Adam with a learning rate of 0.001 and number of epochs 100. But however, we realized that during the training, the model could overfit. So we decided to use early stoppage to avoid model from overfitting, and the training ended at around 58 epochs. And inside here, we have our learning curves, which we attained during the training. So the training results was this: the model performed well as indicated in the confusion matrix. Of the 87 test data set of COVID, all were classified correctly. And 47 test data sets of normal image, all were classified correctly. While of the 100 test data sets of other lung diseases, only one was misclassified as normal, while pneumonia, all were classified correctly, 59. And we achieved rock curves where COVID had AUC of about 1, normal AUC 1, other lung diseases, we obtain an AUC of 0.99, while pneumonia, an AUC of 100. So this one showed that really our model performed very well. However, we also picked sample predictions made by our VGG16 model. And we realized that really the model were using a correct lung features to predict the presence of a disease. Like for the case of COVID, it was able to identify the B lines here, and this image was correctly predicted. For pneumonia, it used some of these bronchograms and was able to predict it, and then the normal used the A lines. Since I've told you that we trained many models, this was the summary of the performance comparison of the 4 models which we trained, with VG16 outstanding at an accuracy of 99.65, and this is much, much better than the clinical acceptable level, followed by VGG model, which is VGG19. Then Inception V3 tied with VG19, while Efficient Net performed least. And realized that why this model performed least, because it required a lot of the data set. So there was disparity in the training, and it gave us a very bad accuracy. So we took up VG model and realized that it's the best performing model. Therefore, since this work is still at the initial stage, we intend now to collect local data for clinical validation in collaboration with Mulago Hospital, and we intend to do classification and localization of the features at the video level. Then that process going through the image frames, extraction, then selection, that's a very tedious process, but we want our model to be in position to classify at a video level, meaning that the user just scans and then it is classified. Then we also need to expand our model to have that explainability ability to give a description to the user why it is performing so and so. And then we also intend now to integrate our model into an imaging pipeline of lung ultrasound. So I need to thank so much my supervisors, Dr. Joyce, Dr. Andrew, Dr. Cosmas, and partners, funders, especially the International Development Research Center, Makerere iLab, CEDA, and then Makerere University Research and Innovation Funds. Thank you so much for listening to me.
Thank you very